Welcome students to this session on operations research. In this session, we will be discussing about the different measures for queuing models. What are the different measures for queuing models? Let us see. First is traffic intensity or utilization factor rho. We have already seen in the previous session. Traffic intensity is the ratio of the mean arrival rate and the mean service rate. So rho is equal to lambda divided by mu, where mu is greater than lambda and rho is less than 1. Average number of customers in the queue. The next important measure is the length of the queue. That is, how many customers are there in the queue. That is given by LQ is equal to lambda square divided by mu into mu minus lambda. Again, lambda is the mean arrival rate and mu is the service rate, mean service rate. LQ is the length of the queue, or the average number of customers in the queue. What is the average number of customers in the system? It is represented by LS. LS is equal to lambda divided by mu minus lambda. Now the difference between LQ and LS is already discussed in the previous session or in the previous slide or previous video. Again, let us again remember, or let us again refresh our memory. LQ and LS. LQ, that is the average number of customers in the queue, or queue length, does not include the customer who is being currently served at the counter, whereas LS includes the length of the system, or the number of customers in the system includes the customer who is being served at the counter. So LS is equal to LQ plus the number of customers served at the counter. At the counter. So here again, fourth measure will be average waiting time of a customer in the queue will be WQ is equal to lambda divided by mu into mu minus lambda. It's the average waiting time of a customer in the queue. Sometimes in problems it will be asked what is the length of the queue and what is the average waiting time for a customer, or what is the average time that a customer will have to wait in a particular queue. You have to use this particular formula. Similarly, average waiting time of a customer in the system, Ws is equal to 1 divided by mu minus lambda. Ws is equal to 1 divided by mu minus lambda. The sixth measure is what is the probability that the queuing system is idle or the server is idle? P0, which means what is the probability that the system is without any customer. So if the system is without any customer, it means the server is idle. That is given by 1 minus lambda divided by mu, or 1 minus this traffic intensity. 1 minus this rho value, or the traffic intensity, will give you the probability that the queuing system is idle or the server is idle. So for example, if the utilization factor rho, the traffic intensity rho, is equal to 0.8 or 80%, that means the system is active or the system is busy for 80% of the time, or the system is always serving 80% of the time. Now then what if suppose if a question is asked, then what is the probability that that particular system is idle, or what is the probability that there are no customers in the system or the server is idle? That will be 1 minus that 0.8 from the previous example which I just told you. So if the traffic intensity or utilization factor is 0.8 of the system, then the probability that that system is idle will be 1 minus 0.8, which will be 0.2 or 20%. That is what this P naught or P0 means. Probability that the queuing system is idle or server is idle. Next, probability of n customers arriving in time t. For example, if the organization wants to know or the service center wants to know in the next 15 minutes, in intervals of say 5 minutes, 10 minutes and 15 minutes, 5, 10 and 15. What is the probability of customers arriving in this 15 minutes duration? The probability of n customers arriving in time t. This is the probability of n customers arriving in time t. That is, say for example, or in other words, I can also say that, say for example, the probability of 15 customers or 20 customers arriving in say 5 minutes from now. Similarly, the probability of say again 15 customers arriving in time, say time can change. That will be lambda t whole raised to n into e raised to minus lambda t whole divided by n factorial, where n is the number of customers arriving in time t. E here represents the natural logarithm, and this lambda here again, these are all same. Lambda here refers to the mean arrival rate, n is the number of customers, t is the time. Eighth one, what is the probability of n customers in the queuing system? Pn lambda by mu raised to n into 1 minus lambda by u, or again I'll repeat, lambda by mu raised to n into 1 minus lambda by mu. It can be very clear here. Whenever we say probability of n customers in the queuing system, this n will be given to you if it is told probability of say 10 customers in the queuing system. You have to substitute n in this particular equation. So P10 will be, if n is equal to 10, then P10 will be lambda by mu raised to 10 into 1 minus lambda by mu, or rho raised to 10 into P naught. Probability of the system being without any customers. Okay? So these 8 measures have to be understood very well, and this will be applied now to specific cases as the case may be, so that you get the measures for the respective queuing models. Let us take a problem. The mean arrival rate at the service center is 3 per hour. The mean service time is found to be 10 minutes per service. Assuming horizontal arrival and exponential service time, find the utilization factor, probability of 2 customers or 2 units in the system, expected number of customers or units in the system, expected time in minutes that a customer has to spend in the system. Now, out of these four now will require the help of the formula which you saw in the previous slide. There were 8 expressions which you saw, mathematical expressions or like formula. So which one to use where, that is important now. This utilization factor, first one is very clear. Your traffic intensity or utilization factor rho is equal to lambda divided by mu. But what is lambda? Mean arrival. It says customers arrive at the rate of 3 per hour, 60 minutes. Per 60 minutes, 3 customers, 3 customers in 60 minutes. So one customer. So per minute, how many? In 60 minutes, 3 customers. In 60 minutes, 3 customers. So in 1 minute, 3 by 60, 3 by 60. 3 by 60 is 1 by 20, that is 0.05 customers per minute. Similarly, the mean service rate mu will be, mean service time is 10 minutes per every customer. It takes 10 minutes to serve one customer. For one customer, 10 minutes. It is 10 minutes per service. So per minute, how many customers? One customer, 10 minutes. Or 10 minutes for one customer. So how many customer per minute? How many customer per minute? 1 by 10. 1 by 10 per minute. So 0.1 per minute. 0.1 customer per minute. So what is the traffic intensity or utilization factor rho? Lambda divided by mu. First bring both this lambda and mu into a uniform unit. Both of them make it now uniform. Both of them now should be in the same units. In this case, it's customers per minute. Mean arrival rate 0.05, 0.05, 0.05 customers per minute, and service rate is 0.1 customer per minute. Traffic intensity or utilization factor rho will be lambda divided by mu, that is 0.05 divided by 0.1, that is 0.5. So 50% of the time the system will be busy, which means 1 minus 0.5, that is another 0.5. The system is idle 50% of the time, is 50% of the time. At the same time, it is working, it is active, or it is busy. There are two things: one is the system being busy, another one is system being idle. Each one is one minus the other. So traffic intensity or utilization factor rho is equal to 0.5 or 50%. Traffic intensity or utilization factor can also be, or rho can also be expressed as a percentage. So this is equivalent to 50%. Next, Pn. What is the probability that there are two units in the system? So Pn, P2, put n is equal to 2 and substitute in the formula given, whatever was there in the previous slide. So Pn, P2, we need to now find out what is the probability that there are two units, or two customers in the system. So P2 will be 0.05 divided by zero point 0.1 whole square, 1 minus 0.05, 0.05 divided by zero point 0.1. So that comes to around 0.125. That comes to 0.125. So the probability that there are two units in the system is 0.125. Third one, expected number of units in the system, that is length of the system. Ls is given by lambda by mu minus lambda. So 0.05 divided by zero point 0.1 minus 0.05, that will be equal to 1. So the length of the system is 1. Length of the system here is 1. So the system length here Ls is when there is one customer in the system. That is there is one customer in the system. Now what is Ws? What is Ws here? Ws is the expected time in minutes that a customer has to spend in the system. Expected time in minutes that a customer has to spend in the system. That is Ws, which is given by 1 by mu minus lambda, that is 1 divided by 0.1 minus 0.05, that comes to around 20 minutes. When you convert it into minutes, you get 20 minutes. So you can see here all the measures using the appropriate formula, mathematical expression, you can arrive at whatever measures are asked here. So utilization factor you have got as 0.5. The probability that there are two customers in the system, 0.125 or 12.5%. Length of the system, number of customers, expected number of units or expected number of customers in the system is 1, and expected time in minutes that a customer has to spend in the system is 20 minutes. Please take this into account. This is the application of the measures of QE. Let us take another problem, a similar problem. In a health clinic, the mean arrival of patients is 12 per hour. On an average, a doctor can serve patients at the rate of one patient every 4 minutes, assuming Poisson arrival and exponential service time. Find the average number of patients in the waiting line of the queue. Average number of patients in the system, average waiting time of patient in the queue, and average waiting time of patient in the system. The mean arrival rate lambda will be 12 per hour. You can see here 12 per hour, which means in 60 minutes 12 customers. 12 customers in 60 minutes. 60 minutes 12 customers. In 1 minute 12 by 60. 12 by 60, that is 1 by 5, that is zero point 0.2 per minute, zero point 0.2 customers per minute. See, even though you cannot have a decimal value of customers from the point of the mathematical calculations, you cannot have zero point 0.2 customers in practice, in actual, no, you consider actual. But for mathematical considerations, you can take it as a decimal here, 0.2, a fraction. 0.2 or 1 by 5. So that will be mean arrival rate lambda will be 0.2 customers per minute. Similarly, the mean service rate mu will be, you can see here, every patient is served, one patient is served every 4 minutes. One patient is served every 4 minutes, which means 4 minutes per patient, 4 minutes per patient. So one patient 4 minutes, 1 by 4 per minute. That is 0.25 customers or patients per minute. Now, utilization factor rho will be lambda divided by mu, that is 0.20 divided by 0.25, that is 80%. So this particular health clinic is busy 80% of the time. So this health clinic, this system, health system is busy 80% of the time, and 20% of the time it is idle. What is the first measure that is asked? Average number of patients in the waiting line or queue, or it is LQ. LQ is given by the expression lambda square divided by mu into mu minus lambda. That will be 0.20 whole square divided by 0.25 into 0.25 minus 0.20, which is 3.2 patients. 3.2 patients. Mathematically, you can say yes, 3.2. You can round it off. Practically, if you are looking at it, you can make necessary arrange. No, necessary, you can round it up. But you are now mathematically you're finding a solution. So LQ will be 3.2 patients. LS. Next, average number of patients in the system. LS will be lambda by mu minus lambda, which is 0.20 divided by 0.25 minus zero point 0.2, which will come to around 4 patients. 4 patients. Similarly, average waiting time of patient in the queue, WQ, will be lambda into mu minus lambda, which is 0.2 divided by 0.25 into 0.25 minus 0.20, which is 16 minutes. 16 minutes. And similarly, fourth one, the average waiting time of patient in the system, 1 divided by mu minus lambda, that is 1 by 0.25 minus 0.20, which is 20 minutes. So very simple substitutions. Whatever is given or is asked should be understood first. Please take care in not applying the wrong formula to a wrong case. Applying the right mathematical expression to the right case or the right situation is important here. So understand the problem. What is asked? Average number of patients in the waiting line or queue. So has to be the length of the queue. Second, average number of patients in the system, length of the system. Average waiting time of a patient in the queue, WQ. Average waiting time of a patient in the queue system, WS. WS. And then substitute the formula and get the solution. So this is a general way of finding out the measures. So these measures are very important from the point of view of service. Any service organization would like to try to reduce the waiting time of the customers. They want customers will be happy, right? Everyone wants to be served quickly. All of us want to be served. Don't have much of a time. All of us are busy most of the times, so we don't want to stand in the queue for a long time. So some attempt is made to reduce the waiting time in queues. So all these measures will help in reducing the waiting time in the queues. The customer's waiting time is greatly reduced. The waiting time will be reduced when the service is faster. The thing is service. When the service is faster, service can be faster when it is like this. No, both are dependent. For example, the service and the arrival rates. That's why we say always arrival rate and service rate. The ratio of that is always less than 1. Lambda divided by mu will always be less than 1. Will be less than 1. Rho is always less than 1. Okay. So let us take one more problem and understand this better. Arrivals at a telephone booth. Arrivals at a telephone booth are considered to be Poisson with an average time of 10 minutes between one arrival and the next. The length of the phone call is assumed to be distributed exponentially with a mean of 3 minutes. What is the probability that the person arriving at the booth will have to wait? It is what the probability that the person arriving at the booth will have to wait. And telephone department will install a second booth when convinced that an arrival would have to wait at least 3 minutes for the phone. The telephone department will install a second booth when convinced that an arrival would have to wait at least 3 minutes for the phone. By how much time must the flow of the arrivals be increased to justify a second booth? By how much time must the flow of the arrivals be increased to justify the second booth? So what is happening here? There is a telephone booth and arrivals are considered to be distributed, Poisson distributed, with an average time of 10 minutes between one arrival and the next. So mean arrival rate is 1 by 10 per minute. That is 0.1 per minute. 0.1 per minute. And also the length of the phone call is assumed to be distributed exponentially with a mean of 3 minutes. That means mean service rate, that is 1 by 3 per minute, 0.33 per minute. 0.33 per minute. So 0.33 per minute is the mean service rate or mu. Lambda is 0.1 per minute and mean service rate is 0.33 per minute. So the traffic intensity or utilization factor ρ will be lambda by mu, which is zero point 0.1 divided by zero point 0.3, which is 0.30. That means 30% of the time this system, telephone booth or this system is busy. So 70% of the time it is idle. So 30% of the time this system is busy. Now the second question asked is, so the first question is, what is the probability that the person arriving at the booth will have to wait? So it's nothing but the utilization factor. Utilization factor will have to wait. What does it mean as to wait? That means the probability of that particular system being busy. So the traffic intensity or utilization factor is 0.3. Probability that a person arriving at the booth will have to wait is the probability that the system is busy, which is 0.3. Which is 0.3. Now, next, the telephone department will install a second booth when convinced that an arrival would have to wait at least 3 minutes for the phone. By how much time must the flow of the arrivals be increased to justify a second booth? The department will install a second booth when they are convinced that an arrival would have to wait at least 3 minutes for the phone. So by how much must the flow of arrivals be increased? So for that, it specifies, the problem here specifies or gives you a value that WQ is equal to 3. That is, waiting time in the queue. Waiting time in the queue is 3. Waiting time in the queue is 3. That is 3 minutes. And mu is already 0.33 per minute. So your new lambda, you have to now find out that q lambda which will satisfy this equation for WQ. You know the WQ expression is lambda by mu into mu minus lambda. Substitute lambda here is WQ is 3. This WQ is 3. Lambda nu you have to find out. Which value of lambda? Your WQ will come 3. That's what you are going to find out now. So 3 is equal to lambda nu into 0.33 into 0.33 minus lambda nu. Now this becomes a quadratic equation. So lambda nu can be solved now mathematically as 0.16 per minute. Lambda nu will be solved as 0.16 per minute. Solve it as a quadratic equation. This will be, you just multiply all this, rearray this as an equation, you get a solution. Lambda nu is equal to 0.16 per minute. Hence the increase in arrival rate. So now the new lambda value is 0.16 per minute. The previous arrival rate was 0.10, the original one. So the increase in arrival rate will be 0.06 arrival per minute. So by how much must the flow of arrivals be increased to justify a second booth? So the increase in arrival rate now is 0.06 arrival per minute. The increase, because the new lambda value is 0.16 and the old value, original value was 0.10. Hence the increase in arrival rate is 0.06 arrival per minute. So this is a slightly different type of problem. Again, analyze the problem clearly and then apply whatever expressions that are related to that. Let us take another problem now. Problem 4. Customers arrive at a bank counter managed by a single cashier according to Poisson distribution with mean arrival rate of 6 customers per hour. The cashier attends the customers on first come first served basis at 10 customers per hour. Find the probability of a number of arrivals 0 through 5 during 15-minute interval. And the probability of the number of arrivals, that is 0 through 5 during 15-minute arrivals. So here the mean arrival rate lambda is equal to 1 by 10 per minute already given, which is 0.1 per minute. Which is why? Because 6 customers in 60 minutes. In 60 minutes 6 customers. In 60 minutes 6 customers. 6 customers in 60 minutes. So one customer in how many minutes? One customer in how much? So that is what you're going to find out. So you 6 customers in 1 hour 60 minutes 6 customers are coming. 6 customers 60 minutes. One customer how many? That's what mean arrival rate lambda will be 1 by 10 per minute. So 0.10 customers per minute. Zero point 0.1 per minute. So 0.1 customer per minute. So you can see it. Very simple. Just substitute this. In 60 minutes, 6 customers. So in 1 minute, in 1 minute, 1 by 10. So 1 by 10 per minute. That is 0.10 per minute. Similarly, the mean service rate mu will be 1 by 6 per minute. Why? Because the service rate is 10 customers per hour. 10 customers per 60 minutes. So 10 customers, 10 customers per 60 minutes. So per minute, 60 minutes, 10 customers. So per minute, 10 by 60. That is 1 by 6. That is 1 by 6 per minute. That is 0.167 customers per minute. And probability of n customers arriving in time t. Probability of n customers arriving in time t is given by lambda t whole raised to n into e raised to minus lambda t whole divided by n factorial. So here probability of n customers arriving in time t is equal to this expression. So you have to now take n values. What is our? Find the probability of number of arrivals 0 through 5. The company now wants to see what is the number of customers, say in the next 15 minutes, probability of no one coming, probability that no customer comes in 15 minutes. Put n is equal to 0 in this expression, t is equal to 15. Put t is equal to 15, n is equal to 0, you will get 0.223. Probability of one customer arriving in 15-minute interval, put n is equal to 1, t is equal to 15. Similarly, probability of two customers arriving in time t, put n is equal to 2, t is equal to 15. Similarly, probability of 3 customers arriving in time t, put n is equal to 3, t is equal to 15. Probability of 4 customers arriving in during 15-minute interval, put n is equal to 4, t is equal to 15. And finally, probability of 5 customers, probability of 5 customers arriving during the 15-minute interval, put n is equal to 5, t is equal to 15. So you will get this probability of arrival in 15 minutes, you will get all these values, 0.223, 0.334 and so on. So these are the different types of measures that you have to now find out to predict a particular queuing model or a particular waiting line model. So these are the different measures. Again, understanding the terminology associated with the queuing models, different characteristics of queuing models, how you represent a particular model, and how you find out the measures. So that are the different challenges that a person in charge of a queuing or waiting line model is responsible or aware of, is involved with. So you have to be very clear here which mathematical expression to be applied to which particular case. Identification of that particular case and then connecting it with which is the mathematical formula to be used to solve that particular problem, that is the key in queuing line models. As already told, all these evaluations become very handy. Say in say restaurant, for example, heavy rush on say weekends, for example, heavy queue management system. Yes, these things are important. This will come handy there. Auditoriums. Go to see a movie. Of course, today it's all online, but no, there are no cases where you may go to an auditorium to watch something at theater. Go and watch theater, plays. You may watch plays. You may watch a musical concert. Go to a movie. You may go to a talk, uh, talk on a specific topic. You may go to a doctor or a clinic. You may be given a token, so you're actually in a queue. Actually, token system, priority ways, token system. So all these concepts will be helpful there. Evaluating the service and the arrival and the service levels at a particular service center. So please keep in mind all these things, and then one by one apply, see the case, apply the appropriate formula, and get the results. That is about queuing theory, the different measures, and where this queuing theory and all these measures are applied. So practice these problems, understand the terms associated with queuing theory, and arrive at the solutions by applying the appropriate formula to the right case. Thank you.